Welcome back to the next class on the deflection of beams and shafts. Today we will try to solve few problems for finding the deflection of the beams. As far as the problems in hand are concerned, we are given a cantilever beam. The cantilever beam is fixed at one end, it has a fixed end, and it is free at another end. Okay, this cantilever beam is free at one end and it's fixed at another end. The length of the cantilever beam is L, its total span is L, and it is subjected to a concentrated load P at its free end. Okay. Under the influence, before we apply the concentrated load on the cantilever beam, the axis of the cantilever beam will be straight. But under the influence of the concentrated load, the beam will deflect at its free end, and the trajectory that the beam will follow, or its curve, what you call as a deflection curve, will have some shape. Okay, we are given, we have to find what is the equation of this curve. Okay, what is the equation of the curve? Initially the axis of the beam is a straight line. Now after the application of the load, the beam will bend like this. This will be the curve the beam will follow. We have been asked to find the equation of this curve. Okay, and we may also be interested in finding how much is the maximum deflection that the beam undergoes, how much is the value of the deflection at the free end. These questions are very easy questions. We can do them like, first of all, we know the equation of the elastic curve is with the equation that we have in hand that we have derived yesterday, EI d2 nu by dx2, EI d2 nu by dx2, this is the differential equation in front of us, is equal to m, where as far as m is concerned, m is the bending moment of the beam. Okay, m is the bending moment of the beam. So first of all, we will have to find, in order to, if we solve this differential equation, the solution of this differential equation will be nu, where nu is the deflection. The solution of this differential equation will be the solution of this differential equation will be the value of the deflection nu. But in order to solve this differential equation, we should be knowing the value of the value of the bending moment. So first step will be finding the bending moment of the beam. In order to find the bending moment of the beam, what we will do, the way we have been doing in our previous classes, first of all, what we will do, we will say let the reaction at end B. First we'll find the reaction. Since this beam is fixed at only one end, that is end B, there will be some reaction at end B, that's what we call as RB. Okay, and we know at the fixed end of a cantilever beam we also have the moment, that is what we call as moment and end B. Once, well, we were drawing the shear force and the bending moment diagram in the previous class, previous semester. We know that as far as a cantilever beam is concerned, in a cantilever beam at its fixed end we have the reaction and we have the bending moment, that's what we call as MB. Now first of all, we write down the equations of equilibrium. The equation of equilibrium will be RA, that's acting RB, sorry, that's acting upwards, and this P is acting downwards, minus P is equal to 0. Therefore we will get, as far as this RB is concerned, this RB will come out equal to P. So we'll say as far as the reaction at end B is concerned, the reaction at end B is equal to P. This is it. Now what we do, in order to find the bending moment at any point, what we will do, we will draw a section. Okay, we'll take a section at that point. Now once we take a section, on that very section we will write, let on this section, let the value of the shear force be equal to V, and let's suppose the bending moment here is equal to M. We have to find the value of this bending moment, M. Okay, now in this section, for this very section, we will write again the equation of equilibrium. The P is acting downwards, we'll write minus P, and this V is also acting downwards, minus V is equal to 0. Therefore we will write V is equal to minus P. So we got the value of the shear force. Okay, as far as the bending moment is concerned, now let's take the moments about an axis passing through point A. Okay, for moments about an axis passing through point A, there will be the moment. Let's suppose this section we are taking at a distance x. The moment, because of V, will be V into x, and it is trying to rotate the beam in clockwise direction, it will be minus, so it will be minus V into x. And the moment bending moment is m, that will be minus, since this is clockwise, this will be minus m, okay, for this very section whose length is x. For equilibrium, this has to be equal to 0. Therefore, m becomes equal to v into x. M will become equal to minus vx. So as far as the bending moment of this cantilever beam is concerned, that's equal to minus vx. As far as v is concerned, v is equal to p. So we'll write this as this equal to minus v is equal to p. It will be p into x. Okay. So this is our uh, this is the bending moment of this beam. So as far as the bending moment is concerned, the bending moment of this beam is equal to minus p into x. So we know, as far as this m is concerned, in place of this m, we'll write minus p into x. Okay. So our equation is now reduced to, our equation gets reduced to our equation gets reduced to we can now write the equation that we have now, that is ei d2 nu by dx2 is equal to minus p of x. Okay. That's equal, we can do cross multiplication and perform integration. Ei, so if we perform the integration, since we have to find the solution, we have to find the deflection, so we have to integrate this equation. Integrating both sides, integrate this equation, we'll get, first integral will give us ei, integration of d2 nu by dx2 will be d nu by dx, one derivative will go, is equal minus integral px will be equal minus px square by 2 plus constant of integration c1. Okay, because this is indefinite integrals, we are taking the constant of integration as c1. Perform integration again, we'll get ei. Okay, ei is constant, it will come out of integration. Integral d nu by dx, we have integral d nu by dx. Integral d nu by dx is equal to nu. So integral d nu by dx is equal to nu is equal minus p by 2. This is integral x square dx, that will be x cube by 3. 3 into 2 is 6. So it will be minus px cube by 6 plus integral c1 dx will be c1 of x plus another constant of integration c2. Okay. So this is this equation that we are getting. This equation gives us the values of the deflection of this cantilever beam for different values of x. You give some values of x, x is equal to 0, we'll obtain the value of deflection, x is equal to 1, x is equal to 3, x is equal to 4. For different values of x, we'll get the values of deflection. So for us, we call this as equation of the deflection curve is equal, nu is equal, equation of the deflection curve is equal, nu is equal to 1 by ei, 1 by ei minus px cube by 6 minus px cube by 6 plus c1x plus c2. This is the equation of our deflection curve. Okay. Now in this equation, we are having two constants, c1 and c2, which are the constants of integration. We have to find these constants of integration. Well, in order to find these constants of integration, what we will do, we can find these constants of integration by, in order to find these constants of integration, what we do, we have to find what we call as the boundary conditions. Okay, we have to find what we call as the boundary conditions. Boundary conditions. What is happening to this beam at the boundaries? These are called boundary conditions. As far as the boundary conditions are concerned, this is, we are measuring our x-axis from, we have taken this to be our origin, free end we are taking as an origin. If we go in this direction, if we go in this direction, this is our x-axis, and here at this point we have, this point is our x is equal to 0, and this point is our x is equal to l. Okay, this is our x is equal to l. Look at x is equal to l, what's happening. At x is equal to l, at this very point where the beam is fixed, the beam will not move down here. The beam will not undergo any deflection. At the fixed end, the beam does not move downwards. That is, at x is equal to l, at x is equal to l, the value of deflection is equal to 0. This is very important. At x is equal to l, at x is equal to l, the value of the deflection is equal to 0. At x is equal to l, the value of the deflection is equal to 0 because the end B is fixed. It neither moves up nor moves down. Number one, at x is equal to L, we have one more condition. At x is equal to L, we have one more condition. That is, they, as far as this line is concerned, the line which is very, very close to this fixed end, these points do not undergo deflection. At x is equal to L, there is no deflection, okay? As far as the line was concerned, as far as the axis of the beam is concerned, initially the axis of the beam was straight like this. Before the application of the load, the axis of the beam was straight. Now, as we are applying the load, what is happening to the axis of the beam? The axis of the beam is now shifting. The axis of the beam is taking this shape, okay? Axis of the beam is taking this shape. If we draw the tangent at point B, if we draw the tangent at point B, if we draw the tangent at point B, okay, that tangent is parallel to x-axis. That is, the slope of the tangent is 0. Slope of the tangent to the curve, slope of the tangent to the curve at x is equal to L is equal to 0, which means slope of the tangent means d nu by dx is equal to 0. Slope is equal to 0. Okay, its slope is equal to 0. D nu by dx is equal to 0. What do we mean by d nu by dx is 0? You draw a tangent at point B to the curve whose equation is nu as a function of x. Okay, we have the equation of the deflection curve is this, which is given by this equation. If we draw the tangent to the curve at x is equal to L, if we draw the tangent to the curve at x is equal to L, the tangent to the curve at x is equal to L, the tangent to the curve at x is equal to L will be parallel to the x-axis. That is, its slope is equal to 0. These two form our boundary conditions. We call these two conditions as our boundary conditions. What are our boundary conditions? Boundary conditions means that at x is equal to L, our deflection is 0. At x is equal to L, d nu by dx is equal to 0. Now, we will substitute these conditions, x is equal to L, nu equal to 0. This condition we will substitute in this equation. And x is equal to L, d nu by dx is equal to 0, we will substitute in this equation. Okay. So as we substitute x is equal to L, nu is equal to 0, we will obtain nu is equal to 0 is equal to 1 by EI into minus P x is equal to L, that is PL by 6 plus C1L plus C2. This is one equation we will obtain. The second equation we will obtain when we substitute d nu by dx is equal to 0 at x is equal to L, we will obtain d nu by dx is equal to 0. It means 0 becomes equal to, at x is equal to L, it will become minus 1 by EI it will become 1 by EI, 1 by EI. This is at x is equal to L, it will become minus PL square by 2 plus C1. Okay, 1 by EI cannot be equal to 0. Therefore, from this equation we will obtain C1 is equal to PL square by 2. So first constant of integration we have obtained. The first constant of integration C1 is equal to PL square by 2. Substitute the value of C1 here, we will obtain the value of C2. From this we will obtain 1 by EI cannot be equal to 0. We will get minus PL cube by 6 plus C1 into L. C1 is PL square by 2 into L, that is PL cube by 2 plus C2 is equal to 0. Therefore, solving this, our C2 becomes equal PL cube by 6 minus PL cube by 2 that becomes equal to PL cube by 3. Okay, so this will become to us, this will be equal to PL cube divided by PL cube. C2 will become equal PL cube minus PL cube divided by 3 minus PL cube minus PL cube divided by 3. So this is the value for C2. Substitute the value of C1 and C2 in this equation to obtain the final equation. Therefore, the final equation of the deflection curve for us will become the final equation of the deflection curve will obtain nu. The equation of the deflection curve, nu is equal to 1 by EI multiplied by minus px cube by 6 plus c1 into x, that is pl square by 2 into x plus c2, and our c2 is equal minus pl cube by 3 minus pl cube by 3. Okay, so this is the equation of our deflection curve. This is called the equation of the deflection curve. Now substitute what will be the deflection at x is equal to 0 at the free end. At x is equal to 0, that is at this free end, what will be the deflection? Substitute x is equal to 0 in this equation. Deflection will become equal 1 by EI multiplied by this term, and this term will cancel. It will be PL cube by 3. But minus, because deflection is downward, so it will be minus PL cube. So deflection at the free end of a cantilever beam is PL cube by 3 times a. These questions are often asked in the gate exams. The deflection at the free end of a cantilever beam is equal to how much? It's equal to PL cube by 3 times a. This is what we had to do. We had to find the equation of the deflection curve, and we had to find the deflection at the free end. If we are given what is the deflection at x at half of the beam at the mid span at x is equal to L by 2, we'll substitute x is equal to L by 2 and obtain deflection at x is equal to L by 2 in the same way. So now this is how we have to solve these problems. In the same way, what you will do, you will go to this question. We have a simply supported beam, or before you do this question, I am leaving this as a homework to you. You will please solve this question, that we have a simply supported beam. We are having a simply supported beam. It is subjected to concentrated load. Okay, we have to find the maximum deflection. First of all, we should be knowing what is the deflection curve. Again, you will use the same formula, EI d2 nu by dx2 is equal to m. Is equal to m. Okay, you will use this equation. Okay, find the bending moment of this beam for this very section. Okay, apply this equation, obtain the deflection curve. Find the bending moment for this very section, obtain this equation, find the deflection curve. I hope that you will at least try this problem at your home, or tomorrow I will myself be showing how to solve these types of problems. Thank you very much.